The abstract functions we've designed so far seem very useful. Lots of list functions feel like map to or filter to. In fact, map and filter are so useful that they're built into the intermediate student language. It provides them as what are called built-in abstract list functions. And in fact, it provides several more built-in abstract list functions. In this video, what I want to talk about is how you can use these built-in abstract functions when you're coding one of your own functions. So we'll look at how to decide which built-in function is appropriate in a given situation, and then how to set yourself up to use it properly. I'm in the using built-ins starter.racket file, and this file just starts out defining some useful data and functions that will let us have more interesting examples below. And now I just want to talk about what some of these built-in abstract functions are. You can get a list of all the built-in abstract functions by going to the course website, going to the language page, which you can always select from here, going to the end of the language page, and here's a list of all the built-in abstract functions. For example, the third one in the list is map, which was the first abstract function we did. And it's got its signature, it's more than one line purpose, and the header, which allows them to name the parameters and write the purpose more concisely. Let's jump back over to Racket and see some of these functions in action. I've got some check expects here to demonstrate them, and what I'm going to do is run them. Now there's going to be a couple failing tests, but those are actually from farther down in the file. These check expects here are working. And I'm actually going to also demo them down here just to drive home what's happening. So I'll take this and copy it and go down in the interactions area. And if I map the predicate positive over a list of numbers, well, I get back the result of calling positive with each of those numbers, which in this case is true, false, true, false. If on the other hand I use filter with negative, I get only the negative numbers -2 and -4. There's an abstract function we didn't abstract before, but I think you'll see what it is pretty quickly. This is folder, and if I call folder with +0 and the list 1, 2, 3, I get 6. Folder is the abstraction of sum and product. Plus is the combination. 0 is the base case result. And that's the list that it operates on. The way to think about it is that folder is filling in the ordinary template for operating on a list of X. So folder in some sense is the abstract function for the list of X template. And we can use it in other kinds of ways. For example, here we're doing the product function that we did before. Now build list is one we haven't seen before. Let's jump over to its documentation. What it says about build list is that it consumes a natural number and a function which itself consumes a natural number and produces x. And this function produces a list of those x's. And what it does is it calls the function, it produces a list of calling the function on 0, ... all the way up to calling the function on -n1. Let me show you that more concretely. I need to tell you first that there's this funny function in Racket which was made pretty much exclusively to use with build list and some other abstract functions. This function is called identity, and all identity does is whatever you give it as an argument, it gives you back. So it's the identity function. It produces its argument. If I use identity with build list, let's say I say build list of 3 and identity, I get the list 0, 1, 2. Because look, what's it doing? It's calling identity on 0, it's calling identity on 1, it's calling identity on 2, and it's stopping there because 2 is 3 minus 1, and it's making a list of those results. Here's another one. If I say build list square on 4, I'll get, I got the arguments backwards. Build list 4 on square, I get 0, which is the square of 0, 1, which is the square of 1, 4, which is the square of 2, and 9, which is the square of 3. Build list is a funny thing. We'll see why we want to use it a little bit later. Here's some problems that are all of the same form. They've all got the beginning of a function design, and they're at the template code the body stage. And what I'm going to show you how to do is how to recognize that this is a case where you could code the body by calling a built-in abstract function. The basic trick is to first kind of get the insight, hey, you know, this feels like it's a fairly generic operation on a list. Maybe there's a built-in abstract function. I wonder which one it is. And after a while, you get pretty good at doing it just kind of automatically. But until then, the way to do it is to compare the signature of the function you're trying to design, here it's list of image to list of image, to the signatures of the built-in abstract functions, which I've got here, minus their function argument. So now I'm taking away the function argument. And so what I'm going to do is compare list of image to list of image to these signatures. Well, it doesn't match the first one. It doesn't match build list because that consumes natural. It matches both of the next two because list of image to list of image matches list of x to list of x. And it also matches list of x to list of y because remember, x and y don't have to be different. They just can be different. And it doesn't match any of the remaining ones because list of image sure as heck isn't Boolean, and the last two functions take 2 arguments. So it's either filter or map, and in this case, of course, it's filter, because this is filtering behavior. We're potentially producing fewer elements in the result list than in a consumed list. That's what filter does. Map always produces 1 element in the result list for each element in the consumed list. So this is a filter, and the way we're going to template it is like this. We're going to say, hey, this is a filter. I won't know what argument to pass it here, but I do know it gets the list here. And now this is the template. Now at this point in the course, you don't really, for your own purposes, need to save the template. Right? Templating is starting to become something that you understand the structure of. If you can write it down quickly, you write it and go, or you copy it from a data definition. I'm going to leave it here just for your purposes so you can understand what we did here today in this video. Let me copy it. And now I'll comment that one out. And now you have to, as usual, fill in the dots. And the question is, what is the predicate that we pass to filter? Again, if I go look at the complete signature for filter, its first argument is a function that consumes x and produces Boolean. Its second argument is a list of x, and its result is a list of x. So this needs to be a predicate here. It needs to be a predicate that consumes x. Now you may not remember this because it went by quickly, but at the top of this file, there's a predicate called wide question mark, which consumes an image, which is what x is in this case, and produces a Boolean. And it produces true if the image is wide. So this is what we want. We'll go back down to wide only, and we'll just put wide question mark in there. And one of the things that's nice about using built-in abstract functions is that your function definitions get really short. And they get really short, they get so short that you might even be tempted to write them on 1 line. The book sometimes calls that a one-liner, but let me note that, you know, what it means to be a one-liner is that it's very short. So that's really still, for all intents and purposes, a one-liner. It's very short, it's very simple, because we used the built-in abstract function. And let me make one more point here about the benefit of using the built-in abstract functions. It's already up here above, but you might not have noticed it before. Notice that I don't have a base case test here. And the reason I don't have a base case test is that the built-in abstract functions are already thoroughly tested. I know that their base case behavior is going to be correct. So I don't really need the base case test for the built-in abstract functions. So when you use one of them, you don't have to follow the normal rule about starting with a base case test. Let me do another one quickly. List of image to Boolean. Are all the images in LOI tall? And I'm asking, are all the images in LOI 1 tall? Let's go look at what LOI 1 is. See, LOI 1 has all these rectangles in it, so they're clearly not all tall. On the other hand, let's see, if I just took 1 and 3, they would all be tall. So let me go back down there and add that as a second test. So now I've improved the setup a bit, and the question is, which built-in abstract list function is this? Let's see, I consume a list of image, I produce a Boolean, I take the abstract list function signatures, I remove their function argument. Which one matches? Well, it's and map or map. And if I go to the language page and look at the description of and map and or map, and map says produce true if P produces true for every element of locks, whereas or is for some element of locks. And unsurprisingly, I probably could have done this without looking here, but since this purpose is, are all the images in LOI tall, this is going to be an and map. So I'll say define all tall LOI and map ... LOI. And this time I'm not even going to preserve the template. I'll just have briefly this template stage, and now I have to decide what goes in the and map, and of course it's the predicate tall question mark. Let's see. That test is passing. The first failing test is after that. First failing test is sum. I'm going to let you do sum as an exercise now, and I want you to go through the whole process I've just shown, compare the signature of sum to the signature of all the other functions. I'm going to give you a hint here though. I do want you to compare the process, but I am going to give you a hint here, which is that the function you're looking for is folder. So go ahead and do this as an exercise, and when we come back, I'll do the last one.